Okay, so you should have started the first part of the class with the Khan Academy video. That was an intro to pressure. It will also be available to you on Canvas, so you should be able to find the link to that YouTube video. The Khan Academy video, to go back and watch it. I think it does a great job of taking intro to pressure and putting it into less than 8 minutes, which is pretty good. So it should cover these things. Okay, so go ahead and take just a few minutes and go over these questions with somebody next to you and see if they have answers to something you missed. So 2 minutes to go over those. All right, so ready? Let's go over a few of these. So we're going to practice conversions. So I'm going to ignore the conversions for now, and we're going to focus on these last few. So one of the questions says, why is it necessary to use a non-volatile liquid in a barometer or manometer? So given the video that you just watched on Khan Academy, one of the reasons why you want to use something that's not volatile, meaning it doesn't evaporate at room temperature easily, is because you want it to stay in the barometer and or the manometer. So the question is, so it doesn't, or the answer is, so it doesn't evaporate. And mercury is a great liquid that does not evaporate. The second one says, answer question 14 in OpenStax textbook, the end of chapter questions, and it is an open manometer question. Okay, so there will be a couple of these on sapling, so I want to practice through one. So if you see the question, it looks like this, and don't judge my drawing. Okay. And you have a manometer, something like this, that's filled with a liquid. And it tells you that the height over here and the difference over here. So the total height is 29.92 inches of mercury. And the difference over here is 6 inches of mercury. Okay. So in open manometer problems, there's two situations. Either the level on the right is going to be lower or higher than the level on the left of my mercury. Okay. So in this instance, because my level on the right is lower than my level on the left, the total pressure of the open manometer system is actually 29.92 inches of mercury minus the 6 inches of mercury. If the level on the right was higher, then this would be an addition. Because it's lower than, it's subtracting from the total pressure in the manometer. So that means that the pressure is 23.92 inches of mercury. And then the question asks you to then convert that to millimeters of mercury. So in order to do that, we're really converting between the English system of inches and the metric system of millimeters, because the mercury is irrelevant. We're just measuring how much mercury is in the tube. So I'm going to set the train tracks up and then let y'all compute, but it'll help you with your sapling. So in this case, it's 1 inch is 2.54 centimeters, and then we should know that 1 centimeter has 10 millimeters in it, so that goes way back to early lessons, and that will give me my answer in millimeters of mercury. So multiply all the way across. Okay. So open manometer questions are on sapling homework, but this should help you with it. All right, so we're going to have some equations. These are our gas laws that we're looking at. And in an equation, summarize the pressure, temperature, volume, temperature, and pressure, volume relationships, and then name them. Okay, we're going to have more in the next lesson. But the nice thing is this is all given in the book. So I'm just asking you to extract that information. And we see that according to Motton's law, that the pressure and the temperature of the one system, they are inversely related. Pressure and temperature, one goes up. They are directly related. So one goes up, the other goes up. And then that is also true about volume and temperature. They are directly related to each other, meaning one goes up, the other goes up. One goes down, the other goes down. And this is called Charles's law. And the last one here is the pressure-volume relationship, which is the only one that is distinct from the ones given here. And that is that as pressure goes up, volume will go down. And this is called Boyle's law. Okay, so the way I like to think about these are real-world examples. So for example, when the temperature is cold outside, and so for the first time once winter starts to hit, hopefully it's cold now. I'm still recording these in September, so I don't know what November weather will be like, but hopefully it's cold. You might have noticed that when the weather started to get cooler that your tire light came on, like low tire light. And that's because the temperature decreased, hopefully. Therefore, the pressure in your tires decreased and caused your low tire light to come on. It's the same reason why if you have been told this, that if you have a low tire light on, it tells you you're told to drive a few miles, because sometimes the low pressure light will go off, and that's because your tires are warming up, therefore the pressure increases. Okay. In Charles's law, volume and temperature, if you've ever left a opened bottle or an unopened bag of chips in a hot car, so in September right now, you might come in and the bottle has swollen, or the bag of chips is swollen because the temperature increased, therefore the gas inside that container swelled and the volume increased. The opposite happens if you put an opened bottle in the freezer. It will shrink down because the volume is contracting, getting smaller, therefore the temperature is also decreasing. Now, pressure and volume are inversely related, and this is breathing. And I feel like this is the easiest example we have because it's your body that gives us this example, but we have to think about what the diaphragm is doing. So, I always do this with you guys. Take a deep breath in. You know that your air volume is increasing, but the reason why that's happening is because your diaphragm, which is just below your rib cage, it kind of cuts your body in half between the top part and your belly button. The diaphragm is dropping down towards your belly button. This is opening the volume. It's decreasing the pressure on your lungs, which allows the volume to increase. And when you breathe out, Your diaphragm is pushing up towards your shoulders. It's increasing the pressure on your lungs, therefore decreasing the volume of your lungs. So think about it again. You breathe in, the diaphragm is releasing pressure, therefore the volume increases. Breathe out, the pressure is increasing on your lungs, therefore the volume is decreasing. Okay? A&P instructors will love you if you can remember this. All right, so let's practice. So we have some conversions to practice with, which are great. This is dimensional analysis. The only thing is you don't need to memorize all of the conversions that you saw in that video. The most important one is the following. Okay, but always remember to look at the cover sheet that you have been given all semester. It's on Canvas, and look at which conversion factors you have. Okay, that's my recommendation. So a typical barometric pressure in Kansas City is 740 torr, and it wants to know what's this in atmospheres, millimeters of mercury, and kilopascals. So let's start at the beginning. 740 torr. We want to convert that to atmospheres. We know that for every 1 millimeter of mercury, that's 1 torr. Remember torricelli. So I know that for 760 torrs, it is 1 atmosphere, 1 ATM. And I'm going to solve that, and you're going to get, you should expect it to be less than 1 because 740 divided by 760. And that is going to be 0.974 ATM. If I wanted to report that with sig figs, because 740 torr only has 2. So now I'm going to convert to millimeters of mercury. Well, that's super straightforward because 740 torr is equal to 740 millimeters of mercury. It's a 1-to-1 conversion. The last one is going from torr to kilopascals. So I'm going to start off with my 740 torr. And if you think back to the video, it's 760 torr for every 101, 325 kilopascals. So 101.325 pascals. Sorry, let me do this the right way. 101,325 pascals is equal to 101.325 kilopascals. Okay, so I kind of cut corners there a little bit. So if I solve this out, I'm going to get 99 kilopascals. So just shy of 101. Okay, so again, check which conversions you have on your cover sheets, but this by far is the one that you need to know. Okay, the kilopascals to pascals usually will show up on your cover sheets. All right, next one. During the Viking landings on Mars, the atmospheric pressure was determined to be about 6.50 millibars, and then it gives you a conversion to ATM. And what's the pressure in torr and kilopascals? I have a little bird bothering me about a snack right now. Go get it. I don't care what you eat. Sorry. Okay, so I'm going to start off with my 6.5 millibars per, and I'm going to convert that. Now the first thing is I don't have a conversion from millibar to atmospheres, but it's a metric conversion. And so if there's 1,000 millimeters in a meter, there is 1,000 millibars in a bar. And now I can use the conversion I'm given in the problem, which will take me to ATMs. Okay, so far we're in atmospheres, but that doesn't answer my question, which is torr and kilopascals. It doesn't really matter which one you do first, but I'm going to go ahead and just convert to torrs because that's the first one it asks for. So 1 atmosphere, 760 torr. Multiply all the way across and divide by 1,000, and we're going to get 4.88 torr. So now I need to convert that to kilopascals, and I'm going to do that by starting with my torrs, similar to how I did up here. Because I know that for every 760 torr, it's equal to 101.325 kilopascals. So multiply across, divide by 760, and that will give me 0.650 kilopascals. Because there are so many different unit conversions for pressure, there's more than one way to solve these problems. It doesn't matter to me if you saw a different route to the end. All that matters is that you can get to the end and solve for the answer. Okay? All right. We are not going to worry about this one. Okay? So we are not going to worry about 504 and question number 16. What we are going to do is focus on our individual gas laws and then practice a few of the problems, or how we would use those individual gas laws. So one way to state Boyle's law is to say that all things being equal, okay, so what are all things? The pressure of a gas is inversely proportional to its volume, meaning as one increases, the other decreases. What is the meaning of inversely proportional? Well, there you go. That the pressure must increase as the volume decreases and vice versa, meaning that the pressure will decrease as the volume increases. Remember breathing. And then what are the other things that are equal? Well, the other things that must be constant are the temperature of the system and the number of moles of gas in the system. Must be constant. So if we think about the formula, we don't see temperature and number of moles in this formula because they are constant. They cancel out. They're the same on both sides. Now, Avogadro's law is technically on the next lesson. Oops, I should spell it correctly. It's technically on lesson number 29. I'm hoping you can't hear the word game that's going on the computer, on the fridge right now, because it's very loud to me. But this will be on lesson 29, but we can go ahead and break apart this question. It says one way to state Avogadro's law is that all things being equal, the number of molecules, so N, in the gas is directly proportional to the volume. We've already seen ones that have directly proportional. So what does that mean? It means that as the volume increases, the number of moles increases, and vice versa, meaning they decrease together as well. And then it says, well, what is the meaning of all things that must be equal? Well, pressure and temperature. So we're always going to have the 4 variables in each of our gas systems: pressure, volume, temperature, and number of moles. So if 2 are being changed, the other 2 must be held constant in these individual gas laws. Okay, so if we go back up, in Charles's law, volume and temperature are changing, pressure and number of moles are staying the same. In Amotin's law, pressure and temperature are changing, therefore the volume and the number of moles are staying the same. Okay, so let's practice this with the question. Now, this one, unfortunately, is the combined... No, it's not. I take it back. This is not. Okay, so what is the temperature of a volume of this 11.2 liters of carbon monoxide at this pressure if it occupies this volume at this temperature and this pressure? So the first thing we need to see is that the pressure is held constant. Right? It's not changing. Therefore, we can actually ignore it. It's extra information. So having done that, we can now see that we're talking about a set of temperature and volumes being compared to another set of temperature and volumes. So what law is this? Okay, if you're not sure, let's scroll back up. This is Charles's law. It's the only one that has volume and temperature, where pressure and number of moles are held constant. So in this case, let's write the formula out again just to make sure we don't make a mistake. So I have 11.2 liters divided by a temperature that I don't know, 13.3 liters divided by a temperature that I know, except I need to convert it to Kelvin. Okay, so I can do that very easily here, or I could have taken 55 plus 273 and done that before. Okay, so now hopefully this looks familiar. The butterfly method was something I learned in school. I don't know if that's what they call it anymore, but that's what I know it as. So you're going to multiply the things on the one wing, set that equal to the two numbers, which is really a number and a variable, in the second wing. Okay, you multiply the two on the left and then divide them by 13.3 liters. Having done everything correct, we could see the liters are going to cancel out, leaving us with temperature in Kelvin, and we should get 276 Kelvin. So let's walk through it, make sure it makes sense. The volume from left to right is increasing. So we would expect that the temperature from left to right should, I hope I can hear y'all saying it, should increase as well. Okay, so from left to right, the volume increases. From left to right, the temperature increases. This is what we expect when we say that things are directly proportional. Okay, hardest part here is making sure you convert to kelvins and that you, like the M1, V1, M2, V2, the dilution equation, that you keep the pairs together. All right, one more. Okay, this says that if a balloon is inflated with 3 breaths of air and has a volume of this at the same temperature and pressure, so temperature and pressure are constant, what is the volume of the balloon if 5 more same-sized breaths are added? Okay, so in this case, we're going to think of breaths as in number of moles. Okay, so if I have V1, N1, V2, N2, they're directly related, and I know that my volume when I have 3 breaths of air is this, and I want to know what my volume is when I add 5 more. So I need to add 5 to my 3. So then I'm going to do the butterfly method. And then I'm going to divide both sides by 3 after I multiply the 2 on the right. And this is going to cancel out the number of breaths. I didn't do a very good job of writing that, which gives me a volume of 2.8 liters. So let's make sure this matches what we expect. We have a volume of 1.7 when we have 3 breaths, and we have a volume of 2.8 liters when we have 5 breaths. So they increase left to right and increase left to right. So it matches what we would expect to have happened. Okay, so this should have been a total of about 32 minutes or so. So you have lots of time to ask questions about the material from today with Dr. Spencer or Dr. Morris. We have, at this point, all that's left is lesson 29, 30, and 31. So there's 3 more lessons left, and the final and cumulative final are very quickly approaching, you guys. So go ahead and take this time to ask questions. Again, all of this YouTube video, the Khan Academy video, is already available to you on YouTube and through Canvas, and also through Dr. Spencer or Dr. Morris, whoever is there today. And I hope all is going well for you guys in class.